Hello and welcome to another video of Learn with Shrand Vasala. Today we'll be learning about second law of thermodynamics, the ability of energy. So in the first law we learn about enthalpy. Most important is enthalpy, and other one internal energy. So internal energy, difference of internal energy, difference of work done. Heat transfer minus work done in the system. And enthalpy is more over internal energy, is difference between internal energy, which is also difference between enthalpy, which is difference between enthalpy plus pressure volume difference. So now let's learn about second law. The second law indicates the limitation of first law. The transfer of heat is an irreversible process. It is impossible to transfer heat from one system to another, which has a higher temperature without supplying external work. In general terms, during the transfer of energy, a part of energy passes through a form that is no longer available for work. But to the engineer, a knowledge of energy, which is enthalpy, is not enough. He must also quantify the ability or reversibility of that energy for a process. A knowledge of the energy ability or reversibility in a process therefore is mandatory. A short background of the development of second law is as follows. So we learn that from Carnot cycle. The Carnot cycle, postulated in 1824 by Sadi Carnot, assumes that an engine or a system operating as an ideal reversible cycle, ideal reversible cycle, okay, between two heat reversible, which is heat sinks in the most efficient cycle possible. Furthermore, the cycle establishes the upper limit in the efficiency of all possible cycles or engines. Because there is no change in enthalpy, heat exchange, there is no change in heat, the net work done by one cycle is equal to the net heat transferred through the system. Okay, fine, हैन. सो त्यो एउटा साइकलमा चाहिँ एउटा ठाउँमा बसिराख्दाखेरि चाहिँ हिट चेन्ज हुन अरे, हैन. सो W equal to Q1 minus Q2. सो जति नै यो यहाँबाट हिट लुज हुन भनेको त्यो Q1 minus Q2 नै W वर्क डन हो. एफिसिएन्सी इज वर्क डन बाई Q1 और Q1 minus Q2 डिवाइड बाई Q1 है. पहिलाको Q1 ले डिवाइड गर्दैन एफिसिएन्सी इक्वल टु T1 minus T2 divided by T1, where T is the degrees Kelvin. For a machine operating between two different temperatures, one higher at the inlet and the other lower at the exhaust, higher in the inlet ma higher and exhaust ma lower garyo bhane, the maximum quantity of work that can be expected from the machine depends only on the difference between the inlet and the exhaust temperature and is independent of the nature of the fluid. Okay, nature of the fluid man dependent hunna. The transfer of heat is delta Q equal to T1 minus T2, where Q is the heat absorbed by the system at T1 and the efficiency of the system is 1 minus T2 by T1. From a practical point of view, since T2 cannot equal to 0 Kelvin or 100% efficiency is highly improbable for any machines or system, conversely a Carnot cycle is reverse and transferring heat to a system which has a higher temperature in the basic process in achieving low temperatures from the liquefaction of gases, and that process demands the supply of external work. At the time, Carnot was completely unaware that the quantity of heat exhaust at T2 was not equal to the quantity of heat supplied at T1. It was about 25 years later, in 1851, that Celsius calculated in a purely empirical manner that the quantity of heat exhausted at T2 was less than the heat supply at T1. He stated moreover that his loss of heat, which is energy, was characteristic as entropy. Okay, entropy terms comes in second law, first law enthalpy. Celsius also stated that the concept of entropy was a function of the absolute temperature. The principle of lost work or unavailability of energy can be a most serious challenge to the engineer for the optimization of any given processes. Accordingly to Celsius, original statement was, it is impossible for a self-acting machine unaided by an external agency to convey heat from one body system to another which is at higher temperature. So what is entropy? Let's learn. Entropy, known as S, entropy is not a property of any system or substance, but rather a mathematical function that quantifies the second law. It is a creation of whether or not a process will take place in accordance with an engineer's design. Furthermore, entropy is not an energy terms by itself. It must be multiplied by the absolute temperature to be equivalent to energy. The product Ts is then equal to the portion of energy in a process that is unavailable and unretrievable for further work. In a simpler form expressed in Dutch, it is the least amount of work that will be necessary to restore the system to the state in which it existed before the reversibility occurred. Dawes also articulated an analogy of entropy as follows. If the individual components of the atmospheric air, such as nitrogen, oxygen, argon, etc., existed in an individual cylinder, it would be stated that the system was highly organized. Before the entropy of that system can be considered as zero, or as a basic point of reference. If, however, the same individual gases were exhausted and mixed together as found in the atmosphere, the system is now highly disorganized. Therefore, the entropy of the system has increased considerably, in fact, to the point that the probability of again separating the gas into the original organized state is highly unlikely without external work being applied. Entropy is a useful mathematical function that quantifies the irreversibility of any process with an understanding of its use. An enterprising engineer can attempt to achieve the maximum reversibility of the system or process by adding the entropy of every subsystem, i.e. compressor, cooling, distillation, product compressor of a process, and by limiting any probable increase of the entropy of each operation. The engineer can increase the overall efficiency of the process. In other words, the engineer can extract the maximum energy available for the system from the system. Hence, the term energy is now used by many practicing engineers. For example, over the years, engineers working on the low temperature separation of air have succeeded in reducing the energy required to produce 1 metric ton of contained oxygen in a mixture of 99.5% purity from 350 Kelvin watt hour per hour to about 270 kilowatt hour per hour, and even, however, which represent a saving of 20%. For a reversible process cycle, the algebraic sum of all heat effects divided by the respective absolute temperature at which the heat transfer occurs is equal to 0. Q by Q2 equal to T2 by T1. So entropy delta H equal to difference in the temperature Q delta Q by T. And now this we'll learn in tomorrow. Okay. Second law is all about entropy. This is very important from this. Hope you understand. Bye bye. Take care.